video is going to be an example, a linear programming example, just kind of a generic example, so it's not a word problem, but it's going to be an example of an unbounded region. And just to clarify, so that you know what I mean by unbounded region, if you have a graph, and let's just say we're in the first quadrant, and you have several constraints, maybe you have this line, and this line, and this line. If the region was everything had to be shaded above all of those lines, you know that your shaded region would be here. And the reason why it's unbounded is because it's not physically enclosed. The shaded region is not enclosed. So of course that's unbounded. It goes on forever, you know, to the right and up and all that good stuff. Versus a bounded region, you know, if you had something that did this and was shaded, you could pinpoint every single vertex in that enclosed bounded. So we've got bounded and unbounded. If you have a bounded region, these 4 vertices that you calculate will definitely give you a maximum and a minimum. And of course they're your furthest extreme points, so nothing can be more minimal or maximum than that point. On an unbounded region, however, if you find, you know, I guess I could highlight your vertices would be here, and here's a vertex. So you have, you know, maybe you find one of those vertices to be a max and another a min, but as you go further out, because it's not bounded, you might actually run into something that makes it bigger and bigger and bigger. So here's the example we're going to look at. Notice, again, a generic example. So you're just given the objective quantity, which means nothing, but C equals 7x plus y. You have 4 constraints. These should look familiar. X and y are both greater than or equal to 0. Definitely puts you in the first quadrant. So my graph off to the right will just be a first quadrant chunk. And actually, maybe just to clarify that, I'll kind of draw in axes. You know, here's the origin. Then we just have 2 equations, so I will use 2 different colors so you can kind of keep track of which line I'm graphing. So I'll start with this one. And if I solve that for y so I can graph it, I would subtract 2x. Then my other line, I will use orange. So to solve for y, you would subtract x and divide everything by 4. So that's negative 1/4 x. 16 divided by 4 is 4. All right, so I have my 2 equations, and before I would graph, of course, beyond the fact that I know I'm in the first quadrant, my y-intercepts are at 7 and 4. And I can easily scale by 1s. So make sure you always put your scale so that it's never a reason to guess. So I'm going to start with the orange line, which has a y-intercept at 4 and a slope of negative 1/4. So down 1 to the right 4, down 1 to the right 4, and down 1 to the right 4. And then it's off my graph, and that's going to be, of course, a solid line. And that's shaded above, and for now I'm just going to draw an arrow so I don't make a huge mess. Then when I graph the blue line, its y-intercept is at 7 and has a slope of negative 2. So down 2 to the right 1, down 2 to the right 1, etc., etc. So there's that line, also shaded greater than, so that one is shaded above. And you can test points if you're not sure if it's shaded above or below. Don't forget the good old origin. If the line's not going through it, you can certainly test that. So my feasible region is where the 2 lines are, their shading would intersect, and since they're both shaded above, the feasible region would be everything above. So in the first quadrant still, of course. So I'll kind of just shade this region. Now keep in mind it goes forever off to the right here, but obviously I can't go off the screen any further, so it is an unbounded region. And I'm going to just use black here to kind of highlight the vertices. Okay, so this point right here is in the shaded region where the 2 lines intersect And then, so I've got, you know, a y axis point, and you know it's gonna, this orange line is gonna intersect with the x axis also, but my graph is off. But that's easy. If I count all the way over to the end of my graph, that's 12. The slope of my line, orange line, was -1/4. So if I went down 1 and over 4 more, I'd be at 16. So you can't see that, but I'm just gonna make a note that eventually where that orange line would cross would be at 16, 0. Another obvious point is this point up here is 0, 7. I think that's pretty clear. The one that's not obvious, unfortunately, is this point where the orange and blue line intersect. So I have to do a little bit of math, and I'm actually just going to go right up here because I can see that I can just do elimination quite nicely. I could also do substitution with these. That's certainly up to you, but I'm just going to multiply the orange line by -2 to eliminate x. And I'll come squeeze my work in down here. So I'm going to multiply the orange equation by -2. And when I add those together, I get -7y equals -25. If I divide by -7, y is going to equal +25/7, which is, you know, about 3.5-ish. So that seems right if you look at the y coordinate of that point. Then I'm going to substitute 25/7 in for the blue equation maybe. It looks like it would be a little bit easier. So I'm going to put 25/7 in for that y. And I'm going to subtract 25/7. I'm going to change 7 to a 7th. So of course 7 as a 7th would be 49/7, and then I'm going to subtract the 25/7 just to get that common denominator. So 49 minus 25 is 24/7, and then I'm going to divide by 2, and that's really like multiplying by 1/2. So x is going to equal, 2 goes into 24 12 times, 12/7. So, sorry, I'm kind of all over the place, but that point right there is 12/7 and 25/7. Now I just want you to think about these 3 points, these 3 vertices that we had, and I'll kind of, sorry about my little tiny graph off to the side here, but I'm going to highlight those points again, and that point is, you know, over there a little bit, but you get the idea. So I'm going to put these into the objective quantity and just, you know, as if I'm blindly going through the motions and see what happens. So my objective quantity right up here, right? So 7 times x plus y, 7 times x plus y, and 7 times x plus y. Okay, then we'll do the math. So 7 times 16 is 112 plus 0, of course it's 112. 7 times 0, 0 plus 7 is 7. 7 times 12 sevenths, sevens cancel out, is 12. So 12 plus 25/7. And I'm actually going to make 12. I'm going to change that to 84/7 because that's still 12. And then 84 plus 25 is 109/7. So, well, okay, so first of all, approximate 109/7 is about close to 15-ish, right? So I know that this point right here appears to be my maximum, and this point right here appears to be my minimum. But I want you to think about it. So now if you go to the point 16, 0, which again, my graph is not out there enough, but again, it's unbounded, so it goes forever to the right. So what if I went to 17, 0? If I put 17 in here instead of 16, what's going to happen to this number? It's going to get bigger. What if I go out to 18, 0, 19, 0, 20, 0? Again, you get the idea. This is unbounded, so this is truly not a maximum point. Okay, so I scratched that thought. I don't have a maximum. And then check your minimum. Maybe you won't have a minimum either. Sometimes you have both, sometimes you have neither, sometimes you only have one. So thinking about your point that makes the minimum, which is 0, 7, what if I go further up the y-axis to 0, 8? Well, 0, 8 is going to get bigger. So that truly is a minimum point. so that's okay. But I did not have a maximum. So there is an example of an unbounded region versus a bounded region. Now, a lot of what you deal with in real life is bounded because your constraints make it that way, but not always.